Tonight is quite informal. We'll step through a little bit of the history and the technology, but I think most people will enjoy getting out and having a little bit of a look at the small UAVs we've got outside, and we'll put up a little bit of a flying demonstration once we're finished as well.
As James said, we're a small group in Canberra UAV. We started late 2010, and the original inspiration was this guy. This guy is Outback Joe, who is a dummy who managed to get himself lost in the middle of Queensland, and over a period of 7 years, teams have been trying to find and rescue him. And he was in an area near Kingaroy, and the teams were told that he was within an area of about 2.2 kilometres by 1.1 kilometres, and the mission was to create an autonomous aircraft which could do an autonomous takeoff, a mission which would need to be about 70 kilometres long, and with a vision system on board which could recognise and find Joe from the air with an aerial search, and then be able to drop a water bottle on Joe like this as a rescue package, symbolising a medical rescue package. And then the aircraft, after having located and dropped a rescue package, needed to fly back to Kingaroy Airport and do an autonomous landing and do all that in 1 hour. Now, that's actually quite a challenge for model aircraft, especially for amateurs. And we got together as part of our local hackerspace in early 2011 and decided we would take it on. And we're really fortunate to have people who have both aerospace background, model aircraft building, software engineering, radio technologies, a whole wide range of engineering specialties who volunteered their time as part of the team. So in the early days, so I'll just go there. So this is CMAC, where we are standing now, the Canberra Model Aircraft Club. That's it from the air. And we're blessed with a really good club here, and the club members have been extremely supportive, and so we do most of our activities here, but we do occasionally fly other flying sites. This is some of the early days. This was one of our very first vehicles we played with, which was a small quadcopter. We were just learning to fly autonomous vehicles, and just knowing the orientation of the vehicle was quite important in the air, thus the yellow duck stuck to the top of the vehicle so we could tell which way it was facing. And this was in the very early days of quadcopters. We got involved right at the ground level in the whole beginning of the drone craze, and we wrote a lot of the software that drives many drones that you see in the shops. If you go down to Harvey Norman and you buy yourself one of those black drones there, in fact it's flying software, where a fair chunk of that was developed by Canberra UAV and is now sold internationally. And this was where we sort of all got started, but we quickly moved on to other things. The challenge, as I mentioned, the idea was to rescue Outback Joe. One of the technical challenges was building a mechanism to be able to reliably and accurately drop a water bottle. And so one of our early experiments was with a water bottle dropping mechanism on a small fixed-wing aircraft. This is a Dragon Lady aircraft, and so we were then doing experimental drops over the area out here. And not all of our flight tests are wholly successful. That was the result of that flight test, where the aircraft ends up in small pieces. So many aircraft have been sacrificed in the name of this effort, but there's also been a large number of successes as well. So we moved on to some other fixed-wing aircraft. This is a small foam aircraft called a Skywalker, which was a stalwart of... So you can also see here we had modifications on the ground station. In this case we were experimenting with a sunlight readable laptop. So we actually cut out the back of the screen of an old laptop there in order to have the sunlight coming through the screen, giving a nice bright image. So there's a lot of areas of technology that we are experimenting with in the project. So we moved up to some slightly larger aircraft. We were really fortunate that a company in Perth donated a larger UAV. You can see this grey military-looking UAV there behind Andrew Moss. Andrew Moss was a team member who's since moved to New Zealand. He was instrumental in getting us involved with one of the local schools, Dixon College. And we had a very good relationship with the school, teaching the students how to fly model aircraft and getting them involved in the student version of the Outback Challenge. This particular aircraft is called a Muggin, and it had a 50cc petrol motor on the back of it and would cruise at about 150 kilometres an hour. It was a little bit overpowered for landing on this 130 metre strip that we have out here, which may explain some of the grey hairs on Jack, our chief pilot. But it was a marvellous aircraft for carrying payload. We had a lot of payload we could carry. In fact, it could carry so much payload that we had spare capacity, and when we wanted ballast up the front, we just used a great big lead acid battery as ballast, which gave us battery as well as balancing out the aircraft. Because it just had so much payload carrying capacity, it was no issue at all. In this particular case, it's a radio being tested in my fridge, because the fridge acted as a nice Faraday cage, and I was looking at with the attenuation of the signal in the fridge, using that to test the range of the radio. Testing radios, this type of radio here can do 100 kilometres as in line of sight, and testing these radios is difficult because it's hard to get 100 kilometres away with line of sight, and so we tend to use attenuation, things like putting it inside a microwave oven, inside a fridge, that type of thing, also putting attenuating antennas on. And this was just one of our little experiments. My wife is very understanding about the types of experiments that are done in our house. In order to test the range, in the real conditions of the real challenge, we had to operate at a range of about 6 kilometres from the aircraft, so well beyond visual range. So some of our testing we did with a safety pilot here at CMAC, but the rest of us sitting at the top of Red Hill, operating remotely, and it's quite an eerie feeling the first time when you're actually operating a UAV 5-6 kilometres away. You can't hear it at all, but you just see it on the screen, the satellite image view, and see it finding Joe and dropping a water bottle from that sort of range. And that was a great preparation for going up to Kingaroy for the challenge. So this is the result of the 2012 challenge. So in 2012 we flew this Muggin, and we were very lucky to win the challenge, but we didn't win the grand prize. So they gave us a consolation prize of $10,000. The grand prize is $50,000. And the reason we didn't win the grand prize is we failed to release the water bottle onto Joe. That's because we had a failure of the bottle release mechanism. And that meant that we did the best of any team in the challenge. No team up to and including 2012 managed to complete the challenge. We went the closest, however, finding Outback Joe with a high degree of accuracy, but not managing to actually drop the water bottle because of a failure of our release mechanism. And we were very proud of the results nonetheless, and the $10,000 we got from that funded the development of our effort 2 years later. The challenge was changed to be every 2 years, and so we were then aiming for the 2014 challenge. We then entered the next plane. This is the 2014. This is the plane we ended up flying, but we developed a number of aircraft in preparation for the 2014 challenge. In particular, a very interesting custom-designed aircraft built by Jack with an awful lot of assistance from Greg, called the Bushmaster, which was a foldable aircraft, very large. Unfortunately, we had an incident a few weeks before the challenge where we lost the aircraft. So we ended up flying our backup aircraft, which is this Porter. And you can see a Porter, the same type of Porter out there on the table, the VQ Porter, 2.7 metre wingspan with a 35cc DLE two-stroke engine. And this is it actually flying in preparation before the challenge. You can see the bottle drop mechanism under there. You can see this little laser rangefinder here, using a laser rangefinder for height above the ground. That's for precision landing, for autonomous landing. And we have this radio mast you can see here that sticks out at the top of the aircraft. That's for the long-range 5.0 gigahertz Ethernet bridge for high bandwidth link, and using this type of radio here, the Ethernet bridge. So in that challenge, we had a van. So we got a van with a large screen in the back of it. And if you want to come up and look later, I'll actually be showing a zoomed-in version. This was our ground station with all the full status. So the aircraft at this point, when this photo was taken, was 6 kilometres away, flying over the search area in Kingaroy, and we were monitoring it, all the imagery and the automatic image recognition status coming up on the screen. And this was just about at the point where we found Outback Joe. So we then found Outback Joe, and now some of you may not be able to see clearly. Down here there's a little tiny yellow object there on the bottom of the screen. That's Outback Joe. So that's the tiny area. You're flying at about 120 metres, 400 feet or so, and you're flying at about 100 kilometres an hour. And the aircraft, the automatic image recognition system, the computer on board has to identify and get the precise coordinates of Outback Joe in order to be able to drop a bottle. And this is our onboard camera looks straight down. It's roll stabilised and looks straight down. And it caught the moment when we released the parachute, and it's put a little blue box around Joe. That's the recognition system saying that looks like Joe. That's what we're aiming for. So it's basically releasing the water bottle to drop on that location. So some of you, it might be a little bit hard to see, so I'll just zoom in there and you can see what it looks like. And you can see some of the challenge. Here, it is a very small object that you're seeing. You're basically seeing like a yellow spray jacket, and in a large area, and quite a varied area. In this particular case, they chose the middle of a peanut field to put Joe, which was particularly kind to the teams, but he could have been in the middle of a bunch of trees. We didn't know, so we had to try and sort him out wherever he was. So we successfully dropped that bottle, and afterwards our plane automatically circled to determine exactly how close we'd got to dropping the bottle on Joe. And the automatic image recognition system continued working and identifying Joe. And in fact, here you can see it's identified. There's Joe, and there's the organisers standing next to Joe, measuring the distance between our water bottle and Joe. So our water bottle, in a 25 knot wind, we managed to calculate the wind drift, etc., to drop the water bottle 2.6 metres from Joe, which was the result of a lot of testing out here with wind drift factors, etc. So we got within a short distance, and so we were very pleased with that. Came back and did an autonomous landing, and this was the result. We won the first prize, and that earned us a $50,000 prize, which of course we then ploughed back into the development, and we've spent more than half of it already towards the next challenge. So onwards and upwards. So the next challenge is this. So this is what we are preparing for at the moment. We are hoping to be in the challenge in September this year in Dalby in Queensland. And the challenge this time has a vertical takeoff and landing component. It's a much longer distance. Previously we had to fly about 6 kilometres away. This time the total distance, the round trip is going to be between 60 and 80 kilometres, and the furthest distance will be about 20 kilometres or so from base. The big difference is that Joe, we know Joe is sitting somewhere over here. We know his position within 100 metres, but we've got to take off from here, fly along this flight path within this green flight corridor. Then we have got to find Joe's position there, and then we must do a vertical landing to land more than 30 metres from Joe. If it's less than 30 metres, you're disqualified, but as close as possible to Joe. So 31 metres would be great. Land 31 metres from Joe. Then we have to shut everything down, turn off completely, and at that point the organisers will place a blood sample on the vehicle and then press a button. And then 1 minute after they press a button on the vehicle has to autonomously start its engine and take off vertically again, and then fly all the way back at around 100 kilometres an hour or so, back along this path, and then land back at the flying field. And all of that has to be done within 1 hour. So the big challenge this time is the fact that it must be vertical takeoff and landing. There is no runway at the destination. So that means we have to have an aircraft that can fly at around 100 kilometres an hour for around 45 minutes and do vertical takeoff and landing. And for those of you who know about model aircraft, that's actually quite a significant challenge because there's lots of aircraft that can do about half that, but it is very, very hard to find an aircraft that is affordable and that can do that challenge. So we are looking at a number of solutions for that. And this was one of our first experiments. This is a senior telemaster quad plane. So it is a standard RC model that you often see at model flying fields called a senior telemaster, model from the 1940s or so, I believe, very old model in style. Then we have strapped a quadcopter to this so it can take off vertically. And this was actually quite successful. We did manage to fly it a number of times, but it was very complex to fly, and we in fact had an accident due to just the procedures of coordinating between a separate pilot for the quadcopter part of the aircraft and the fixed wing part of the aircraft. So we moved on, and we ended up with this aircraft, which you can now see here. This is a Quadstar, which is a relatively cheap model aircraft, again with a quadcopter strapped to it. Now this aircraft does not have the range and the endurance or the speed to do the Outback Challenge. It's an experimental aircraft that is just for demonstrating, the types of capabilities and the development of the software. So we've been developing the software to fly this type of aircraft, and we're going to be doing a flight demonstration of this aircraft today, doing a fully autonomous mission. So it'll do a vertical takeoff from the runway, then an autonomous flight, and then a vertical landing. Please be aware that this is a highly experimental aircraft, so if it crashes, we learn something. And we're always learning things about our aircraft. It is very experimental code, but it has done 6 or 8 successful flights, so we're very pleased with it so far. But as I said, it isn't of a scale that can actually do the challenge for us. It's just a small test aircraft, and we are also developing helicopters. This is Shazza, which is a JS-90 helicopter that's been converted to a petrol engine from an original nitro engine. And Shazza, in fact, is sitting out on one of the tables out there. You can see Shazza, but Shazza, I believe, doesn't have her canopy on. So this is Shazza with her canopy on the front. And Shazza has been a very successful test aircraft in helicopters. The next scale up of helicopter is the GX9 from Gowie, and we're very pleased to be partnering with Gowie, and they've provided us with the aircraft at a great discount. And Greg in particular has been working closely with Gowie on the development of this aircraft and the deployment with the autonomous, so the flight controller. So it's got a Pixhawk flight controller fitted and is capable of fully autonomous flight, and we are hoping that it will be doing fully autonomous flight this weekend, in fact.
When you say autonomous, what are you meaning?
Well, we can press one button and it will then spool up, take off, fly a mission, come back, land, shut down with one button.
One button.
One button, that's it. Yes, one button plus some very nervous operators.
And a lot of pre-programming.
That's right, we put in a mission plan, and I'll show you the mission plan we're going to do for one of our planes in a second, what that looks like. But yes, we put in a set of waypoints, a set of conditions, the airspeed we want, the heights we want, what we want it to do. We program all that into it, and then it can operate fully autonomously. But at all times we have a safety pilot holding one of these who is able to take control for full manual control. Plus we have the ground station operator operating a laptop like this who is able to command it to, for example, come home, land, shut down immediately, crash, for example. So we've got special code in there for deliberately crashing the aircraft when that is needed. And that is one of the requirements of the Outback Challenge, that you must be able to demonstrate that you can safely terminate your aircraft if necessary. So there are strict geographic boundaries, etc., and conditions under which you have to terminate the aircraft and crash it into the ground. We do an awful lot of simulation, a lot of software development and simulating the aircraft, simulating the vision system, the automatic image recognition, plus the flying in different weather conditions, etc. We converted it a few weeks ago to being a quad plane and flew it very successfully as a quad plane. Until right at the end of the flight, so I'll show you the flight as a video in a second, right at the end of the flight, as it was descending for the final landing, one of these failed. And a heat sink, it turned out that there was a mistake in the factory with the heat sink, and that caused a field effect transistor to fail in one of these speed controllers. That made the quad plane turn from a quadcopter into a tricopter, which doesn't work, and the plane descended into the ground. But I'll show you that to give you an idea of the types of experiments that we do. So this is the aircraft taxiing out to for a vertical takeoff here at CMAC just a few weeks ago. And so that's the forward engine, the 35cc petrol motor. This is under control of Jack. Feel free to come further forward if you want to see it more clearly. Apologies for the small screen, we don't have a projector here, unfortunately. So in a few seconds it'll start up its vertical motors, which are 4 of these 18-inch propellers. So it's got a 20-inch forward propeller with a 35cc petrol motor. Then it's got 4 of these propellers are vertical and giving it a total of 10 kilowatts of vertical power for a short period of time. It needs that for the 15 kilogram aircraft. It's rather unusual to see an aircraft like that take off vertically, those of you who are used to model aircraft. It then takes off vertically, and then it transitions, and the software deals with the transition and keeping the aircraft stable as it goes to forward flight. When the front motor starts in a few seconds, and you'll see it spin up, there it goes with the front motor starting, and it then starts speeding off at full speed, doing its mission. It goes up to around 100 kilometres an hour, and by this stage the vertical motors have stopped completely, and so the batteries are now idle. It's just the petrol engine that's drawing the plane along. And it then does a number of laps of the area before transitioning back to a vertical landing. Transitioned correctly to a hover, was starting to descend vertically, then one of the ESCs unfortunately failed, and at that point it then crashed into the ground, and we were very sad to lose that aircraft. One of the unique things we've developed is the full autonomy and the image recognition system to be able to automatically find people in a search and rescue scenario. So what I'm going to demonstrate here is, if I turn this on, then you'll see these are the real images coming from the Outback Challenge 2014. So this was the competition flight. And this is the live still images coming in accelerated time from our onboard camera. Most people who do UAV type search and rescue, what they tend to do is they try to just look at this image stream. And it is an extremely difficult task to look at that image stream and find anything. Basically you need to stop and pause all the time, and the human brain just isn't designed to be able to process this. So we don't do that. We have that available if you want it, but we never look at it. Instead, we just put that away, and what we look at is something far more relaxing, which is this view. And this view is the processed view from the onboard camera, where it is automatically finding objects within the search area that it thinks may be of interest to the operator. So it basically sifts out and reduces the amount of data by about a factor of 1,000 down to a very, very small little thumbnails of objects that it thinks are distinctive. And it has a number of heuristics, or works out what a distinctive object is. And you can see that it's found a number of objects here. It's found, for example, here there's a water tank, and it's decided this water tank is interesting, it's distinctive, so it shows it to the operator and says, is that of interest? And if it is, we can say, yes, go and investigate that further. And so what it's now doing, the plane here, you can see, is flying this mission over Kingaroy, and it's just found Outback Joe. So here is Outback Joe, and if we look at the image there, and there's our first view of Outback Joe, just as he comes into view at the top of the image. And let me just zoom that in. There, right at the top, there's Joe that it's found. Notice it's put a little blue box around him. Right, like that, it's automatically recognised. That is of interest, and it gives them a score. And it gave that a very high score because it thinks that object is right on the sort of thing we're looking for. We describe what we're looking for with our image system in all sorts of ways, in colour space and size, X, Y dimensions, area, all sorts of different ways we describe the objects we're looking for, and then it ranks the things it finds according to those scores. Our aim as a group is to develop amateur UAV search and rescue technology. And all of our work is open source, so all of it is released as we develop it to the world for free. We are a non-profit group here in Canberra, relying on both our prize money and on donations to fund our activities. What we're going to be doing now is moving to this aircraft, which is the Quadstar, which is a little bit fancier than the Ranger in that it can do a vertical takeoff and landing. Wait for the VTOL? All right.
2628.
Okay. It's 2628, is it?
Yes.
At that point, it will be ready and we'll do a takeoff. approach, what it will do is it will fly to the south, and it will then turn a long way down there. It's heading down towards the southern part of the field. Now I must emphasise this is going to be the first strong crosswind landing we have done with this aircraft. So its behaviour in a crosswind is going to be interesting. I expect it's going to have some trouble keeping its tail properly aligned. It's now approaching the transition point. It'll come along towards the runway and then it'll switch to vertical mode. It's now switched to vertical mode and it will now attempt to land at the correct position. It'll reposition itself. No, it's not managing to reposition itself correctly. That's a failure actually. There's a fixed wing autonomous takeoff and a fixed wing autonomous landing. We could do that now. Would people like to see that? Okay, we'll do that one. So that was a fully autonomous takeoff and it's now tracking doing circuits. And notice that it's traveling at about a 45-degree angle. So it's automatically calculating the wind conditions and adjusting for those. And it's now going to turn and go along here, again crabbing to cope with that wind. You can see it flying at about a 45-degree angle. That looks reasonably on track to me. And it's now correcting, notice it's going more straight. Fully autonomous landing.
See that one? This is by a very simple one. Tractor, which is.
It has a autopilot up here, which you notice is mounted on an anti-vibration system. Helicopters vibrate. They're basically flying vibration machines, and you really have to isolate them a lot. So we have a really good isolation mount with a lot of mass, some lead weight under there to give it plenty of mass in the isolation. It also has a 3-axis gyroscope. It's an unusual arrangement, as this is the type of gyroscope that, say, 3D helicopter pilots would use, which do just the low-level rate control of the swash plate and the tail. And then the autopilot is controlling that, acting as the pilot for the 3-axis gyroscope. It then has a GPS here for positioning and velocity. Velocity is actually very, very important out of the GPS, not just position. And all of that goes through to allow the helicopter to do autonomous takeoffs, full autonomous missions, and then autonomous landings. What we're just doing at the moment is removing the blades for safety. And once we remove the blades, because they are basically samurai swords that spin at 2,000 RPM, or about 12 or 1,300 RPM on this particular one, which can be quite dangerous. They're made of carbon fibre and they can really slice through you quite in a nasty way. So we thought we might remove them just so we don't have too many trips to the hospital this afternoon. Then Greg's going to be using the transmitter to start the engine remotely. And we won't actually be flying this today. We've been rebuilding this helicopter and fitting it out for full autonomy, and our first test flight of this particular vehicle for fully autonomous flight we're hoping will be this weekend.
So we're going to make sure the ignition is off for that. We have a red light on the helicopter just here which indicates that live ignition. I'm going to remotely disable it. I don't know if you can see that on this side, but there is one. Trust me, we're going to close the choke, and as Trish said, we'll have this automated later. And we're just going to prime the ignition now. So, they'll prime the engine, choke off, and ignition on. Clear the helicopter. A little bit more throttle. So we've just got these engines back from service, so we haven't had a chance to tune the motor. So basically we're just, running it up.
Luckily for the competition, once it's landed, the engine will still be hot. It should start a lot more easily in the remote location. It will only have been turned on for a couple of minutes, which should make it easier. Got more information on the Canberra UAV website. Just go to canberrauav.org.au, you can find a lot more information.
Ladies and gents, thank you all for coming out. I hope everybody enjoyed it. You're certainly hitting those marks and has got us off to a really great start. The team here at Canberra UAV, Andrew, Red, Jack, James, Red. All of them.